In the last few videos in this series, we've been looking at some of the mathematics needed to discuss quantum entanglement, and we're nearly there. We now have our four-dimensional Hilbert space, which we can use to describe a pair of electrons, A and B, and as usual these relate to the spins of the electrons being either up or down in the Z direction. These are the four states where we have the A electron depicted in amber and the B electron in blue. Although we're now tending to write them without the Z subscript, as we should be used to the idea that these basis states always relate to the spins being either up or down in the Z direction. These are the basis states in Hilbert space for any two-electron system. Any pair of electrons could have some mixture of these states. In particular, we began in the last video to look at three separate situations. For the situation where we had two independent electrons, we introduced the idea of the product state. There was very little of interest for us here. This state for the two electrons looked a bit unusual, but it was essentially just like having two independent electrons. Nothing of interest to us, at least as far as entanglement is concerned. Secondly, we looked at the situation where the spins of the two electrons are connected in some way, and their spins are in the same direction. They're entangled with one another in what is called the triplet state. Although much could be said about this state, it wasn't considered helpful to go through the mathematics, but rather to move on to the much more interesting case where the spins of the two entangled electrons are in opposite directions to one another, if you like, when the spins balance out. This is called the Singlet State, and is probably the most sensible one for us to discuss in more detail as an entangled state. It's certainly the most relevant to the way in which we posed the early question of entanglement way back in video number 1. If you recall, we started by thinking about two small bar magnets. When these were allowed to come together, they became what you might call classically entangled, in the sense that they align themselves in opposite directions to one another. This was their lowest energy state, with their magnetic moments pointing in opposite directions. I pictured it like this, although other oppositely pointing situations could be imagined. Even when carefully pulled apart, they remained entangled, in the sense that if you knew the direction of one, you knew the direction of the other. Obvious. We then talked about electrons having a magnetic moment, and in the classical sense, if they were brought together, we said that they would line up in a similar way, with their magnetic moments in opposition, because that was the lowest energy state. In saying this, of course, we're not only ignoring the electrostatic repulsion of the two negative charges, but also other important aspects of physics, like indistinguishability, antisymmetry, the Pauli exclusion principle, and Fermi-Dirac statistics. Now, if those things are totally unfamiliar to you, don't worry. We're treating these electrons simply as two spins, which act like two small magnets. That's our classical analogy, but we're treating them via quantum mechanics, and that's where the magic of entanglement will be seen. I'll show them here with their associated magnetic moment vectors, the red arrows, but to reduce the clutter, I'll take away the indication of the rotation of the electrons. Again, once these electrons are carefully separated, we said that if you knew the direction of one, you would know the direction of the other. They are opposite. The electrons would be entangled, at least in the classical sense. My point about giving that reminder is that we are now about to think about a two-electron system where the spins of the electrons are in opposition. This time, however, we hope to be able to think about it not so much in terms of classical physics, but in terms of quantum mechanics, and get to appreciate something of the mystery of quantum entanglement. I'll take away the arrows from each electron because, as we'll see later, it's not really possible to imagine definite directions for the two separate electron spins. I'll just add the words spins opposite at the side, simply to remind us that even though we won't be able to put definite directions to them, the spins of the two electrons in this entangled state, this singlet state, are opposite to one another. The first thing to reiterate, I suppose, is that the total combined spin of this composite system, these two electrons together, is 0. The two spins balance one another out. whether we're thinking about spin angular momentum, h bar over 2, and the like, where I used blue arrows if you remember, or whether we're thinking in terms of spin magnetic moment and using only integers, where I used red arrows. The total is 0, either way. Here's the illustration of that for the magnetic moment in what we might call the integer version. It's a very boring picture. The total spin of the pair together is 0. This means we have no spin vector that we can put in the picture and ask for its component. It's 0. It also means that whatever spin component we try to measure of this combined thing, x, y, or z, or any other direction in space, we will always get the answer 0. Obviously. In other words, you can try to measure the spin components of this electron pair combination in any way you like, but you will always get the answer 0 in any direction. Now that's fair enough, I suppose. The two spins have balanced one another out, so that you'd think even classically the total spin must be 0 for the combined system, and so any component of it must obviously also be 0. Measure the spin like this, 0. This, 0. This, and this, all 0. I hope you're remembering that I'm using the word spin in that general sense rather than being specific about angular momentum or magnetic moment, and I'll continue in that vein. The next question to ask is, how can we write down the quantum mechanical state of this two-electron system? What is the state vector? We have our basis states, which we understand to apply to our two electrons A and B when considered together. So how can we combine some of these four things to create a state which will represent this particular entangled state, this singlet state? Well, in a similar way to the 0 component of the triplet state, it would seem that this singlet state must involve equal amounts of what we might call upness and downness, which in that way would imply a permanent 0 measurement. We can't say that A is definitely up and B is definitely down, or that B is up and A is down, so it's not just either one of these basis states on its own. Again, I will simply write down, without qualification, what quantum mechanics says should be the shorthand for the singlet state, namely 1 over root 2 times up down minus down up. Or we could write it, of course, this way. It is, once again, a simple mixture of up-down and down-up basis states, normalized by having the 1 over root 2 as the coefficient of each basis vector. There are two things to notice about this, however. First of all, the fact that the coefficients are 1 over root 2 means that if we were to measure the spin component of A or B electrons individually, there is a 50% chance of finding A up and B down, and a 50% chance for A down and B up. The second thing to notice is that this state is very similar to the 0 measure in the triplet state, the middle state, which I quoted as 1 over root 2 up down plus down up. However, this singlet state has a minus sign between the two parts instead of a plus sign. As I mentioned earlier, I don't intend to discuss the triplet state in any more detail. You can study it if you wish yourself, as long as you realize the difference between the triplet and the singlet states, a sign, plus for the triplet and minus for the singlet. For now, as I say, we will stick with the singlet state and explore this in more detail. It is in many ways more straightforward than the triplet state, and it does link quite nicely to our initial discussion about classical entanglement using bar magnets and the like. It should also be enough for us to gain a reasonable appreciation of quantum entanglement. So, once again, we are imagining, in very simplistic terms, two electrons somehow becoming entangled so that their spins are in opposite directions to one another. And here they are, drawn at an angle to the vertical, to emphasize the fact that they can be in any orientation in real space. Now I need to be careful here. This is not a good way to draw an entangled pair of electrons, and you'll see what I mean in a minute. But for now, however, I will carry on with this classical type of picture where I'm showing their line of orientation. Bear that in mind. Okay, we're saying that the two electrons A and B have been brought together so that their spin magnetic moments interacted. In that way, they minimize their magnetic interaction energy by adjusting their spin orientation so that they were in opposite directions, just like two bar magnets. They became an entangled state. Even if these electrons are then separated, they will still be in an entangled state. Now, even if it's incorrect to say so, it probably seems logical to most people to say that their spins, which I'm showing as the red arrows for spin magnetic moments, should be in some definite direction in space. We may not know that direction, but classical common sense says that each should have a direction, and electron spin B will be in the opposite direction to electron spin A. If one is like this, then we'd expect the other to be like this. If one is like this, then the other surely is like this, and so on. We would probably say that any angle in space is possible, but the electron spins must be in opposite directions. That would be classical mechanics. That would be a classical argument. However, even what little we've done so far of quantum mechanics would also suggest that as well. We looked at that very thing for a single electron and proved that there must be some definite direction in space for a single electron, even if we don't know which direction it is. And when I say definite direction, I mean a direction in space where if the component of the spin were to be measured in that direction, it would definitely 100% give the answer of +1. And so here, with this singlet state, it seems reasonable, even if incorrect, to say that each of the two entangled electrons should have some definite direction in space, and electron B will have its spin pointing in the opposite direction to electron A. Now, I've laboured that point because, as we will show in a few minutes, this is not actually the case for this singlet state. Granted, the entangled electrons A and B definitely have spins in opposite directions, and we'll show that, but they each don't have a definite direction in space. There actually isn't a direction in space in which, if you measure the component of the spin of one of the electrons, would definitely 100% give the answer of +1. In that sense, you can't say that the spins in an entangled pair like this have a spin direction. Now that, from our classical standpoint at least, seems very strange. But that's quantum mechanics for you. However, before we demonstrate these facts from the mathematics, let's just remind ourselves what options are on the table for any mathematical measurements we can make on this entangled state. Firstly, we could try to use the mathematics to measure the separate spin components of each of the two entangled electrons using the sigma operators. In other words, we could apply, say, sigma AX onto the whole of the singlet state and see what happens. This would be trying to measure the spin of just the A electron. It might give the same state multiplied by a real constant, in which case we would have a measurement of the X component of the spin of electron A. Alternatively, of course, it may not give the same state in the answer, and there would be no measurement. We could, of course, do that for all 6 sigma matrices, 3 for electron A and 3 for electron B. And any results might just help us to see what's going on with this singlet state. Secondly, we could try to use the mathematics to measure the components of the total spin, using the sums of the sigma operators for a particular direction. In other words, we could apply, say, sigma AX plus sigma BX, that whole operator, to the singlet state and see what happens. This would be trying to measure the spin state of both electrons together, the component of the total spin of the singlet state in the X direction. Again, it might give the same state multiplied by a real constant, in which case we would have a measurement of the X component of the total spin of both electrons together of the state. Alternatively, of course, we may not get the same state in the answer, and no measurement would be the result. And once again, of course, this could be done for all 3 directions, X, Y and Z, of the total spin. In other words, sigma AX plus sigma BX for the total spin in the X direction, sigma AY plus sigma BY for that in the Y direction, and of course sigma AZ plus sigma BZ for the Z direction. Thirdly, we could work out the average value or the expectation value of each of the 6 sigma matrices for this singlet state. You should recall that using the first option I mentioned and making separate measurements via the sigma matrices will often not lead to a measurement. You only get a measurement if the state vector is an eigenvector of the operator and everything works out nicely. Often, however, the spin operator will simply change the state and we're left with nothing, at least in terms of a measurement. This can happen, for example, when we have some kind of mixed state, so that what we're trying to measure has a certain probability for one answer and a certain probability for another. In that case, of course, the mathematics cannot supply a definitive answer, and what sometimes came to our rescue in situations like that was the idea of the expectation value or the average value of the operator with that state. If, to put it crudely, the actual value is flipping from one thing to another and can't actually be measured, it's reasonable to ask the question, what is the measurement on average? And this average measurement, or expectation value as it can be called, may be helpful in understanding what's going on, and so it could be helpful with this singlet state. And once again, we could work out the expectation values of all 6 of the sigma matrices. And if you remember, we write an abbreviation for the expectation value by putting angled brackets around the operators in question. We've done this kind of thing before, and we will look to calculating these particular things shortly for the singlet state. So there are the 3 options. Let me now go through each of these 3 procedures that we have available to us for investigating this singlet state with respect to the components of the spins of the electrons in it. As we do it, we'll see that it will slowly increase our understanding. No, perhaps I shouldn't use that word. It will increase our appreciation of quantum entanglement. So first, let's think about using the sigma matrices to operate on the singlet state. I'll give you the result straight away before we check things, and the result is that if we try to use quantum mechanics to make a measurement of the components of one of the spins A or B in the X, Y or Z direction for the singlet state, we get no measurement at all for any of the 6 possibilities. It tells us nothing. For example, consider sigma AX on the singlet state, where we try to measure the component of the spin of the A electron in the X direction. Early on I said that it was important to know what the sigmas do to the basis states for the single electron. That is what we need here. Here is the table that we had in that situation. You should recall how to interpret these relationships and transfer them from the single electron situation to this entangled pair. For instance, sigma AX only acts on the A electron, and it will change an up to a down or a down to an up, and it will multiply incidentally by +1. Sigma AX on the singlet state therefore gives this. Here the A up has gone down and the A down has changed to up. The B electron, of course, has not been affected in any way. Looking at our result, it's obvious that this is not the same state as we started with. Down down and up up are not what we started with. We have no measurement. This is of no real help to us. The same will be true, of course, for any of the sigma X's and sigma Y's, whether for electron A or electron B, because again, recalling the rules for using the sigmas, sigma X and sigma Y simply flip their respective electron spin with or without adding an I or a minus sign or whatever, so none of these will be of any help. None of these 4 will be of any help. We will always get a new state with down down and up up, and therefore no measurement. Well, what about the sigma Z's then? Can we get a measurement from them? They behave a bit differently from sigma X and sigma Y when working in the Z basis, so they may be more helpful. If you recall, they don't flip a basis state, they measure the basis state, leaving it the same state-wise, but multiplying it by either +1 or -1, depending on whether it is up or down. So what do the sigma z's do to this combination of basis states that make up the singlet state? Let's try sigma az. This will leave the A up state the same and multiply it by +1, exactly the same. It will also leave the A down the same, but multiply it by -1. There's the extra minus. This here is obviously positive, and looking at the whole new state that has been produced, it is not the same as the original. So again, no measurement and no help. If you think about it, we can say the same thing about sigma bz. It will change the overall state and so will not give a measurement. And this means that all 6 separate sigmas, when applied to the singlet state, do not give a measurement. They are not really of any help to us used in this way. At this point, in a sense, we know nothing more about the singlet state than we knew before. How about our second option then? This would be to look at the action of the sum of the sigma operators in a particular direction on the singlet state. Take, for example, the addition of sigma ax and sigma bx. This operator should enable us to measure the component of the total spin in the x direction. Now you might think that this, being simply the sum of the two operators that didn't give a measurement, probably won't give anything either. But in fact it does. It gives us something, albeit fairly trivial, but it does give us something. This sigma ax plus sigma bx is essentially the operator for measuring the component of the total spin in the x direction, the sum of the spins in the x direction. And if you think about it, if the two spins in this singlet state are always opposite to one another, the total spin in any direction should always be 0. This operator, acting on the singlet state, ought to give a measurement of 0. Let's see if it does. Let me apply this operator to the singlet state and see if we can get a measurement of the x component of the total spin of these combined electrons A and B. Clearly, looking at the expansion of these two brackets, the operation of this operator onto this singlet state is going to give us 4 ket vectors in the bracket, 4 terms if you like. Sigma ax on this will flip the up to down because it acts only on the A electron, and on this it will flip the down to up. The sigma bx will act in a similar way. This down will go up and this up will go down. This means that the new expression with the 4 terms in will look like this. Sigma ax has produced these 2 terms and sigma bx has produced these 2. Now if you look at all of this carefully, you'll see that pairs of terms balance out. These 2 give 0 and these 2 give 0. So the total answer is 0. In other words, the application of the sum of the sigma x operators onto the singlet state gives 0. Now this is a result. This is a measurement. This is like getting the same state multiplied by a real number, but the number is 0. So we've used the mathematics of quantum mechanics to make a measurement of the component of the total spin in the x direction of this singlet state, and we got the answer 0. If you like, the singlet state of these 2 electrons A and B is an eigenvector of the total spin operator for the x direction, and the eigenvalue is 0. Now in a way that shouldn't surprise us. We know almost by the definition of the state, as we created it, that the total spin of the 2 electrons added this way in opposition is 0. We've simply checked that is true for the component of the total spin in the x direction. Moving on, it shouldn't surprise you that the same result would be obtained for the y and the z directions. The mathematics might look a little different because the sigma y's not only flip the spins but also bring in I, whilst the sigma z's don't flip the spins but can throw in a plus or a minus sign. Here are the workings out if you're interested. First, for the component of the total spin in the y direction, again 4 terms which end up giving 0. And this is the component of the total spin in the z direction, with 4 terms again adding up to 0. So the upshot is that all 3 measurements of these operators on the singlet state are exactly as expected. The component of the total spin measured in any of the 3 directions x, y and z are each 0. If you think about it too, it means that by simple addition of the matrices to form new matrices for other directions, the component of the total spin measured in any direction in real space must be 0. And once again, this is not an unexpected result for the singlet state. It seems clear from what little we know of quantum mechanics that this should be the case for the singlet state. Okay, 2 down and 1 to go. We've looked at these 2 types of calculation for the 2 electrons A and B in the singlet state. The first, trying to make a measurement of the components of the spin of each electron separately, told us nothing. It wouldn't give us a measurement. The second, just now, trying to make a measurement of the components of the total spin of the 2 electrons together, told us that the value is always 0 in any direction in space. What we're still lacking is any information about the individual electrons A and B when in the singlet state. So let's try our third option. Let's look at the expectation value or average value of each of the 6 sigma operators for this singlet state. In an earlier video, number 6, when dealing with a single electron in some kind of mixed state of up and down, where no measurement could be obtained from the direct use of the operators on the state, we turned to the idea of measuring what we called the expectation value or the average value of the operator with that state. In our case here, we could use it to ask the question, what is the average of the component of the spin of one of the entangled electrons in a particular direction? The actual spin direction may well be here, there and everywhere, and we couldn't get a measurement, so that we may not be able to pin it down to an actual fixed value or direction, but what is it on average? And then, if we needed to, we could do the same for the other electron. Just to reiterate, we know that the actual spin of the whole singlet state, both electrons together, is 0 in every direction, even when they're separated. So the likelihood is that the average spin of the whole state is 0. But that need not necessarily mean that the average spin value for each separate electron is 0 in all directions. It may be that electron A could have an average value of 1 in a particular direction, and the B electron would have an average value of -1 in that direction. In other words, they'd be opposite, making the overall average 0. And that's what we're testing here. What is the average value of the component of each separate electron spin in each of the 3 directions, x, y and z? So, you should recall that the expectation value of an operator is written like this. And we said that the way to find that expectation value for a particular state vector is to sandwich the operator between the state written in 2 ways, the bra vector of it to the left and the ket vector of the same state to the right. In our case, we would like to check out each of the 6 sigma operators, 3 for electron A and 3 for electron B, and see what kind of measurements we get for each one's average value for this singlet state. We'll take sigma AX first. Let's be clear. We are asking here for the average value of the X component of the spin of the A electron when it's entangled with a second electron, namely it's in the singlet state. We need now to put in the ket and bra for the singlet state. Everything in this state is real, so there's no difference in the way the bra and ket look. The complex conjugate, the one that goes as the bra, is exactly the same as the original, the one that goes as the ket. The 2 1/√2s can be taken outside of everything as a half, and I've added extra brackets to clarify things, so the substitution becomes this. We have the bra version of the singlet state, up, down, minus, down, up, and the ket version of the singlet state, up, down, minus, down, up, and we are taking the expectation value of sigma AX. If you remember, the first thing we need to do is to evaluate the action of the operator sigma AX on the ket vector. Now this is easy enough. In fact, we did it a few minutes ago. it changes up to down and down to up, but only for the A electron, with no changes to the signs of the basis vectors, and it gives this. Notice that sigma AX has gone from the middle, and the ket on the right has been changed to down down minus up up. All we need to do now is evaluate the multiplication of these two brackets. As you can see, it will give us 4 terms, and each term comes from a kind of multiplication. Actually, it's more than just a multiplication. We essentially have 4 inner products of the basis vectors. So let's think through them. Up down is orthogonal to down down, so that inner product gives 0. Up down is orthogonal to up up, 0 again. Down up is orthogonal to down down, 0, and down up is orthogonal to up up. They're all 0. So the whole thing, the expectation value of sigma AX for the singlet electron is 0. Now that is interesting. The average value of the X component of the spin of the A electron when in the singlet state is 0. I say it's interesting because suppose we could have said that the A electron spin was pointing even somewhat in the X direction, perhaps at an acute angle to it. We would have expected a non-zero result for this, something greater than 0, maybe less than 1, but greater than 0. What we found in this answer of 0 is almost equivalent to the classical statement which might say there is no spin component of the A electron in the X direction. But as we'll see in a minute, there's much more to it than that. It's worth adding, I think, at this point, before we check the other directions of the sigma A's, that this is not an eigenvalue equation. This is not a direct mathematical measurement where an operator has given the same state multiplied by 0. So getting the answer 0 here doesn't mean there's been a measurement of the spin component. As we discussed in that earlier video number 6, the expectation value is a different kind of thing than that. It is an average value. Okay, so now let's look at the other two directions, Y and Z, again just for the A electron. For Y, it is almost exactly the same calculation as we had for X. The average value of the Y component of the spin of the A electron when it is entangled with a second electron, namely in the singlet state, is given by the sandwich of sigma AY between the bra and ket form of that singlet state. We need once again to evaluate the operation of the sigma AY on the state. Remember that sigma AY flips the A electron but throws in an I and a minus I, so we get this expression. Once again, however, all the bra vectors on the left are orthogonal to those on the right, and so the answer is 0, regardless of the presence of the I's and the different things. In other words, the average value of the Y component of the spin of the A electron in this entangled state with B is also 0. In simple language, its spin doesn't point in the Y direction on average either. Certainly didn't point in the X direction on average. It now also doesn't point in the Y direction either. Finally, what about the Z direction for the A electron? What is the average value of sigma AZ for the singlet state? Again, we sandwich this time sigma AZ between the two versions of the singlet state, bra and ket. To evaluate this part of things, we need to remember what sigma AZ does to the basis states. It looks only at the A part of it, of course, and measures it. In other words, it leaves the up and down as they are, no flips, but it multiplies either by +1 or -1. Here's the result. There's the up multiplied by +1, and there's the down multiplied by -1. It gives an extra minus sign. This time, things in the left bracket are not orthogonal to things in the right bracket. We have the same basis states present on each side. We have work to do, but not much, working through the various inner products. Up down with up down is 1. Remember, our basis states are normalized. Up down with down up is 0. They're orthogonal. Down up with up down is also 0. And down up with down up is 1. But we have 3 negative signs, so that makes -1. giving the answer to be 1 plus 0 plus 0 minus 1, which once again is 0. In other words, the average value of the Z component of the spin of the A electron when entangled with the B electron in the singlet state is also 0. In fact, we have now found that the average value, or the expectation value, of all three of the sigmas for the A electron are 0 in the X, Y and Z directions. Also, I suppose it should be obvious that if we did exactly the same exercise for the expectation value of the component of the B spin in the three directions X, Y and Z, we would also get 0. This is, or should be seen as, a striking result, in my opinion. Let me go through what we've found. Remember, we are considering two entangled electrons, A and B, which are in the singlet state. Their spins are opposite to one another, and these are the three things that we looked at. Number 1 told us nothing. When we operated with any of the 6 sigma matrices, say sigma AX on the singlet state, we didn't get a measurement. The state got changed, and it wasn't a nice, neat eigenvalue equation. And the same was true for all of the 6 sigmas. We could not make a measurement of any component of the spin of either electron. Number 2 told us something, but what it told us was fairly obvious. We operated on the singlet state with things like the sum of the sigmas for A and B in a particular direction. For example, sigma AX plus sigma BX. This gave us a nice eigenvalue equation. So we got an actual measurement of the sums of the spins A and B in the particular direction, X in this case, and the answer was 0. In fact, we got 0 for the total spin measurement for all three directions in space, X, Y and Z. And we said that this again was an obvious result because the entangled state, the singlet state, was more or less set up with the spins of A and B in opposite directions. The third test was the bombshell, in my opinion. So get this into your head. We looked at the expectation value, or the average value, of all 6 of the sigma matrices individually. 3 for electron A and 3 for electron B, and they were all 0. Why do I suggest that this was stunning? Well, in simple terms, this is all saying that the spin of electron A can't be said to be pointing in any particular direction in real space when it's in the singlet state with B. The fact that the average values of all three components of A spin in the X, Y and Z directions are 0 means the average value of the component of the spin of A in any direction must be 0. Why do I say any direction when we've only checked X, Y and Z? Well, the argument is that in a way these 3 sigma matrices for electron A are like 3 vectors in real space. If we say that the average of each of them is 0, then however you add them up to produce a value in another direction, it must also give 0. And the same, of course, can be said for electron B. We cannot say that either of these electrons individually has its spin pointing in any particular direction in space. That's what's strange. Now you may well say, well, quantum mechanics is strange. And of course that's true. But when we were considering the single electron in an earlier video, number 7, even though there were weird quantum mechanical issues about the mixing of states, and even though despite how the electron was prepared, you could only ever get the answer +1 and -1 for the spin, or strictly plus h bar over 2 or minus h bar over 2, one thing became clear. We came up with the conclusion that for a single unentangled electron, there has to be some direction in space where if you measure the component of the spin in that direction, you will definitely get the answer +1, 100% of the time. In a sense, the unentangled single electron does have a definite spin direction in real space. There would be no uncertainty about what you get as an answer, providing you happen to pick the right direction, the direction in which the electron spin was pointing. Granted, if you picked a different direction, there was a chance that you'd get +1 or -1 in that direction. But because the unentangled single electron had a kind of definite direction in space, then if you hit the correct direction with your measuring device, you would be guaranteed to get the answer +1. If you recall, we even demonstrated that fact mathematically. We considered an individual electron not entangled with another one in the general state, which in terms of its spin and using our Z basis of states in 2 dimensions was written like this, where A and B, the coefficients, could be complex numbers and had to satisfy the normalization condition A star A plus B star B is 1, or in simple terms A squared plus B squared equals 1. We then use the idea of the expectation value or the average value to show that this state simply had to have a definite direction of its spin in real space. And to do this, if you remember, we worked out the expressions for the average value, the expectation value of each of the 3 components, sigma x, sigma y, and sigma z of this single electron. And we tried to adjust the values of A and B to see whether it was possible to find values of them that would allow all 3 expectation values to be 0. And the upshot of this exercise was that it was impossible to find values of A and B which would make all 3 of these calculations of the average for sigma x, sigma y, and sigma z equal to 0. We concluded unequivocally that a single electron must have its spin pointing in some definite direction in real space, in the sense that if the component of the spin was measured in that direction, we would always get the answer +1, 100% of the time. In other words, we showed mathematically that for a single electron, and by that I mean an unentangled electron, it must always have a definite spin direction in real space, even if we didn't at the time know what that direction was. That's quantum mechanics for a single electron. Now contrast that with an entangled electron in the singlet state, where, say, for electron A, the mathematics is telling us that the expectation value of all 3 sigmas are equal to 0. This means there is no direction in real space that the electron spin can be said to be pointing. The entangled pair is not like this, with, say, their magnetic moments pointing in a definite direction, like the Z direction. It's not like this, or this, or this, or this. If we insist on picturing it at all, then perhaps it's more like this, with the magnetic moment pointing in no direction and every possible direction. This is my best effort to picture this as a lot of red arrows. I could blur it, but I think I'll leave it like this. You should think of this finite number of little red arrows as really being an infinite number, because in a sense each entangled electron points in every direction in real space and in no direction. The main thing to realize is that there is no direction in space, in real space, such that if you measure the component of the spin of one of the electrons in that direction, you would definitely get the answer +1, either for electron A or electron B. Instead of that, it would always be a 50-50 thing, +1 or -1. Why 50-50? Well, we'll see that in a minute. But the mathematics will show us that if we measure the component of the spin of one of the entangled electrons experimentally, it will give us an answer. But that answer has a 50% chance of being in the direction you're measuring and a 50% chance of being opposite to that direction. That means +1 or -1. There is no preferred direction. And if you think about it, the mathematics of the singlet state itself tells you that this must be true. The singlet state is a mixture of 2 of our basis states, up, down, and down, up. And you'll notice that I've added the Z subscript here to remind us that up and down are in the Z direction. The 1/√2s for the coefficients of each part of the singlet state not only normalize the state, but also mean that there is a 50% chance of getting this and a 50% chance of getting this from any measurement in the Z direction. In other words, if we were to be measuring the component of the spin of electron A in the Z direction, there would be a 1/√2 squared chance of it being up and a 1/√2 squared chance of it being down. However, and this is the magic of entanglement, if after measuring we find that the spin of electron A is up in the z direction, it means that we must be dealing with this up-down part of the state rather than the whole thing. And that means that the component of the spin of electron B must now be down. You could say that after such a measurement the state vector collapses to just the up-down basis state. Similarly, if instead we happen to get the measurement of the z component of the spin of A to be down, which is the other 50% of our chance, then it means that B is immediately known to be up, and the state vector could then be said to have collapsed to the down-up basis state. But here's another intriguing aspect of this. This idea doesn't just apply to the z direction of up and down. It's fairly easy to show that the singlet state of two entangled electrons can also be written in terms of left and right. This is what you get if you churn through the mathematics. The singlet state is 1 over root 2 up down minus down up, but it's also 1 over root 2 times right left minus left right. Notice that it's exactly the same looking formula, with right instead of up and with left instead of down. Again, I've shown the subscripts z and x to emphasize the point. The two things here are identical mathematically. Right left minus left right is identical to up down minus down up. If you don't believe that, here's a quick illustration of how to show it from the mathematics. If you recall from way back, going back to a single unentangled electron with only a two-dimensional Hilbert space, etc., the right and left states could be written in terms of up and down like this. And we can, of course, write this for each of the separate electrons A and B, which means there are 4 such equations. The right state of electron A when it's on its own is 1 over root 2 up plus down for the A electron, and the right state of the B electron when it's on its own is 1 over root 2 up plus down for the B electron, and so on. But if you play around with these equations, then these equations, each pair can be rearranged so that instead of right and left being the subject, up and down can be the subject of the equation. Doing this, you find that up and down for the A electron can be written as functions of right and left, and the same is true for the B electron. Remember, this was for single isolated unentangled electrons A and B. Now let's get back to our 4-dimensional state system for the 2 electrons together. Consider the singlet state that we've been focusing in on, the entangled state of up, down, minus down, up. If you recall, this up-down basis state was created by multiplying A up and B down, and similarly for the down-up basis state it was the down state of the single electron A multiplied by the up state of the single electron B. You may recall that we had a kind of cross-tabulation. So, if in our singlet state, instead of writing the up-down basis part of it like this, we write it as the multiplication of up and down, and if we do the same for the down-up basis, we get this expression. And if we then substitute for the ups and downs in terms of lefts and rights from our previous rearrangement, play around with the mathematics, and it eventually boils down to this. The singlet state is 1 over root 2 times right left minus left right. So this is identical to this, the up-down version. It looks the same as the up-down version, but with left and right. Perhaps that's some of the mathematics I should have left out. It is just a case of churning through it if you want to be sure of what's going on. Anyway, the upshot, of course, which I could have simply stated, is that the singlet state, which we've been saying is a mixture of up-down minus down-up, can also be written as a mix of right-left minus left-right. It's exactly the same thing mathematically. This means that if you measure the component of the spin of the A electron in the x direction, there's a 50-50 chance of getting +1 to the right and -1 to the left. If you do get +1, which is to the right, you are dealing with this and not that. so the spin of electron B must be pointing to the left. This would mean that the state had collapsed or changed to right-left at the moment of measurement. I'm sure you realise that the same exercise could be done for the y direction. It's once again just a case of churning through the mathematics, so that the very same singlet state can also be written in terms of in and out in the y direction. It's 1 over root 2 times in out minus out in. Or you could do the same thing for 45 degrees to an axis, or indeed for any angle to any axis, in other words, in any direction at all in space. And perhaps this different kind of shorthand says it all. The singlet state can be written in a multitude of ways. Up, down, up, right, left, right, this way, that way, whatever, and so on and so on. These, and in fact I suppose an infinite number like them at different angles, are all the same singlet state, and that fact can be shown mathematically. This emphasizes the point made earlier that, in a sense, singlet state entangled electron spins have no specific direction in space. This means that if you pick a direction and measure the component of one of the singlet state's electrons in that direction, you could get the answer +1 or -1 for that electron. There would be a 50-50 chance of either. If you get +1 for that electron in that direction, you can guarantee that if you measure the component of the spin of the other electron in that direction, you will definitely get -1. In other words, once you measure the component of the spin of the first electron, then the second electron's spin direction suddenly becomes fixed, at least in terms of measuring it in that direction. The state vector, or the wave function, collapses to the simpler looking state. Of course, if after the second electron spin becomes fixed you measure the component of its spin in a different direction, then the usual rules of quantum mechanics will apply. For example, if you measure the second electron at right angles to the direction it was now fixed to be in, then there will be a 50-50 chance of +1 or -1. That should be reminiscent of the Stern-Gerlach experiment result. So even though before any measurement was made, each electron cannot be said to have its spin in any particular direction in space, once a measurement has been made of one of them, then both it and its partner can then, at that instant, be said to have definite spin directions, even if they've travelled extremely far away from each other, possibly millions of light years. Let me stress that. They're entangled in the singlet state. They've travelled light years apart, and they each have no definite spin direction in space, and yet, the instant you measure the direction of the component of the spin of one of them, the other becomes fixed. Now, at this point in the discussion, I believe that if you've never come across entanglement before, you need to let this idea sink in. Before questions start to come into your mind which start with the words, "But what about?" just ignore them for a moment and let this sink in. Think about it. Two electrons with spins and magnetic moments got caught up with one another in a fairly understandable way, at least classically speaking. Their magnetic moments, or perhaps I'll just loosely talk about their spins went in opposite directions to minimize their combined energy. They became entangled with one another. And that's where quantum mechanics came into our thinking. Their spins were in the opposite direction to one another, but you can't say what those directions are. That's what seems so strange to our classical way of thinking. You can't say what direction each of the electrons' spin is aligned in. It's almost as though they don't have a direction, or they have every direction in real space. You can separate these entangled electrons by millions of light years and you still won't be able to say either of them actually has a direction that the spin is pointing in. It's an entangled state. It's the singlet state. Measuring the component of the spin of either one of them in any direction gives you a 50-50 chance of getting +1 or -1 for the spin in that direction. That much is clear from the 1 over root 2's in the form of the singlet state, but that's also what would happen in practice. Pick any direction for either electron and there's a 50-50 chance that you'll get +1 or -1. If, however, you do choose one of the electrons, say electron A, and you choose a direction in space, and you make a measurement of the component of the spin to get one of those 50-50 chances, and say it comes out as +1, that means that the measured spin is suddenly in that direction. From having no direction, the spin is then that way. Also, instantly, the other electron spin will have a definite spin direction opposite to that. If that second electron then has its spin measured along the same direction, then you are guaranteed to get the answer -1. Nothing 50-50 about it. The spin direction is opposite to that of the first electron. If, of course, you measure the component of the spin of the second electron at some angle to the direction it's now in, then the usual rules of quantum mechanics that we discussed earlier will apply. Measure is at 90 degrees to its direction, and it's 50-50 whether the spin is in that direction or opposite. If you measure at 45 degrees to its now known direction, then the probabilities are closer to 85-15 that you will measure the spin to be in the direction you're measuring in, that's +1, or opposite to that direction, -1. Having got those ideas to sink in, the question that probably arises in everyone's mind is, how does the second electron know? We start, according to the mathematics, with neither electron having a definite spin direction, and we then measure electron A. If electron B unquestionably has no definite spin direction but gets a definite spin direction once electron A is measured, then what's going on? They could in principle be light years apart by this time, and yet it would seem the instant electron A is measured, the spin direction of electron B is definite. Well, I'm sure you're beginning to realize that this is part of the strangeness of quantum entanglement, and I hope you can see that this is an extra layer of strangeness to what we considered some time ago when we thought about pseudo-quantum mechanical issues surrounding entanglement. If you've forgotten, let me reiterate those simplistic arguments around that halfway house to quantum entanglement, and after that I'll develop things a little further. At least from the way I've discussed entanglement, there could be said to be three ways of looking at the issue, only one of which is correct in terms of quantum mechanics. I call them classical, pseudo-quantum mechanical, and quantum mechanical. If you remember, the straightforward classical way of thinking about entanglement of two electrons is to think of them as being like two little bar magnets. Electrons A and B are brought together and their magnetic moments interact to minimize the energy. They could, of course, be angled at any angle, but whatever it is, their direction would be fixed in space in classical physics. They would each have a direction and be opposite to one another. They're then separated, we suggested, and if you measure one of them along its axis and get +1, then it's obvious that measuring the other one along the same axis would give -1. We start the experiment again, and this time you pick a different direction, which according to this classical idea is at some angle θ to the direction the spins are in, then the result of the component measurement would be cos θ, again plus or minus, and in that case less than 1, as we're considering classical arguments. Still, however, those components would be opposite to one another, all fairly obvious classical ideas. We know, however, that that's not what happens in practice, so consider our next model. In what I call the pseudo-quantum mechanical approach, a kind of halfway house, we imagined the same coming together, then separation of two electrons A and B. Once separated, they were still treated as individual electrons, which each had a definite spin direction, and once again those spin directions were opposite. Measure the components of those spin directions along that direction, if you could possibly know it, and of course once again they will be found to be opposite, +1 and -1. So far no different from the classical way of thinking. However, knowing what we found from the Stern-Gerlach experiment, we had a dilemma if the component of the spins were measured at some angle to their supposed actual direction. The obvious example to take was 90 degrees. Classically, The answer for this component would be 0. But we know from the Stern-Gerlach experiment that the answer will be plus or minus 1 in the measured direction, with a 50% chance of either. Our dilemma was that if electron A has its spin component measured first, say at right angles to its actual direction, which of course we wouldn't know, and if it gave the answer plus 1, how would electron B know to give an answer of minus 1 when it is measured in that direction, when strictly speaking it should have been a 50% chance of plus or minus, just like for the A electron? How could it do this unless there was some sort of shared information or communication between the two electrons? If the shared information or communication did not exist, we would be forced to say that only in one particular direction, the direction in which the electron spins were supposedly pointing, could you guarantee to get one electron with plus 1 and the other with minus 1, which would be not too unlike the classical idea. However, experimentally, things don't work out that way. You can choose any direction for the A electron and it will give plus or minus 1, 50-50. Then providing you choose the same direction for the second electron, you will always find that the spins are in opposite directions. Some other explanation is needed. Things are even more magical than this pseudo-quantum mechanical approach would indicate. And that brings us to our more rigorous quantum mechanical explanation, and to the place that we've been working towards in all these videos. As we waded through all of the mathematics of the way in which two electrons could combine in terms of the state vector which describes the pair, we realized that electrons A and B, when they come together with spins opposite, must be in what we called the singlet state, a highly entangled state. Mathematically, this singlet state, apart from the normalizing factors, is, put simply, up down minus down up, or it could be written right left minus left right, or in out minus out in, or any pair of directions you like, as long as they're opposite. They're all the exact same way of writing the singlet state that the pair of entangled electrons are in. There is no specific direction to either of the electrons. So here's our very classical looking picture of what we have. We're drawing the electrons as spinning charged spheres with mass, and we're illustrating the magnetic moment from that spinning charge as a red arrow, which we're now calling just the spin. We've said before, of course, that this is not a good picture, in that electrons are actually believed to have no size, and as point-like particles they just have a spin magnetic moment as well as a spin angular momentum. We're also ignoring their electrostatic repulsion and a few other physics principles simply because we want to concentrate on their spins. Our state vectors only contained information about their spins. Anyway, before entanglement, the two individual electrons, each with their own definite spin direction in space, are assumed to come together. In simplistic classical terms, when their magnetic moments interact, they line up, sort of, so that their spins are in opposition. But from quantum mechanics, we have to say that there is no specific direction to that opposition. This picture is simply an illustration to try to show that, to show in some strange way we can think about there being an infinite number of red arrows on the electron in all possible directions, which are their possible magnetic moment directions. We then imagine that the now entangled electrons are separated. The individual spins still have no definite direction in space, and yet the spin of electron A is opposite to that of electron B. Now that seems a strange statement to make, but that's what quantum mechanics is saying. They are obviously connected or entangled in some very special way. It's as though they are part and parcel of the same thing, one big state vector, the singlet state. The pair is like a single entity, and yet, at least in terms of being measured, it seems as though they are identifiable as separate particles. But are they? Some people like to picture them like this, with the state vector, or what one might call the wave function of the pair, spread out in space, even if it's spread out over very large distances. We've not considered where the electrons are positioned or how fast they might be moving. Our state vector was only concerned with their spin. But physicists talk in terms of this singlet state as being non-local. The two particles are, in a sense, everywhere, and they could even be said to be together everywhere. From our simple spin analysis of the singlet state, we simply consider that even when they are separated, the two electrons still form the singlet state. And while they're in this singlet state, if you were to make a measurement of the components of the spin of electron A in any direction, you would either get +1 or -1, 50-50. On the other hand, you could instead make a measurement of the component of spin of electron B in any direction, and again you'd either get +1 or -1, 50-50 in that direction. However, as soon as you make a measurement of the spin component of one of them, say electron A, then instantly electron B is such that if someone measures the spin component of B along the same direction, then they will get the opposite answer. How does the second electron know at that instant that it should behave in that particular way if measured? Does information go from A to B? It seems as though it does, but does it? Although we've not yet looked at experiments which support all the assumptions that I've been making about what will happen experimentally, this is how it is. And we'll look at the experiments that show this later. But the fact that this is how it is naturally raises questions in the minds of most physicists when they first learn about entanglement. Questions like, if it is some sort of communication, what's the nature of it? Waves of some sort? And if that communication can go faster than the speed of light, what about relativity? Put naively, the question might be asked, after the first electron's measured and the component of its spin is found, say, to be +1 in the direction being measured, how can the second electron know immediately what direction its spin is to be in? Let's face it, it could be an extremely large distance away from the first electron, and nothing can travel faster than light. Well, the real answer to that question lies in the fact that the two entangled electrons are part and parcel of the same state, the same entity, the singlet state. Before any measurement, it's not really relevant to think in terms of the two particles being separated in space. It can be argued that the state vector for them is all over the place. It's non-local. It's only when you make measurements that you find their spins can be shown to be aligned in opposite directions. The act of measurement collapses the state vector and destroys the entanglement. The current assumption is that when the spin component of one of the electrons is measured and the state vector collapses from, say, this, 1/√2 up down minus down up, the state of the pair of electrons should be treated as a single entity. In a way, there aren't two electrons, there is one state, the singlet state. The whole thing just changes instantly when a part of it, electron A, is measured. And this collapsing of the wave function, or the state vector, when it suddenly changes from something uncertain, A up or down, B down or up, to something more definite, A definitely up and B definitely down, is known as the Copenhagen interpretation of quantum mechanics. There are other possible interpretations of quantum physics that don't collapse the state vector in this way, but the Copenhagen interpretation is currently the most popular amongst physicists, and no experiment has yet been done which could be said to disprove this way of thinking. Now, by now I'm sure you're beginning to see that the introduction to entanglement in video number 1, where we considered bar magnets coming together and then separating as two distinct entities, has nothing to do with quantum entanglement. With magnets, we can talk about them separating from one another by large distances. With entangled particles, all we can say is that the state vector is somehow spread out over large distances. Nowadays, virtually all physicists are entirely comfortable with this idea of the collapse of the state vector, and they don't need convincing that the entangled state of two particles is like a single entity, so that any measurement made, even if we think we're making it on a single particle, is made on the whole state vector. However, at this stage I won't entirely abandon the idea of communication between the entangled particles thought of as being separate, because the experiments that we will discuss in video 12 will sometimes check whether or not any supposed communication travels at greater than the speed of light. We'll say more about all that later. Finally, for this video, let me consolidate some quantum mechanical ideas by considering whether different results would be obtained if A spin was measured first and B second, or B spin was measured first and A second. If you think about it, these should have the same probability for an equivalent measurement, so let's see if quantum mechanics gives that. Consider two electrons in the singlet state, so that the state vector is, as usual, given by 1/√2 times up down minus down up. Or of course we could write it in lots of other ways, such as right left minus left right, and so on. Suppose A is measured first in the z direction, but then B is measured at an angle theta to the z direction. We obviously can't talk about the spin measurements afterwards being opposite, but we can ask the following kind of question. What is the probability of getting, say, A measured as +1 in the z direction and B measured as -1 in the theta direction? What is the probability of a 1 and a -1 on these instruments, and would the answer be any different if A or B were measured first? Now that should be easy to calculate. First of all, consider the situation where A is measured first. The probability for A to be measured as 1 positive in the z direction is 0.5. That is standard for the singlet state, which can legitimately be written like this. And the half, of course, comes from the square of the coefficient of this term, which shows spin A is up. After that measurement, the state collapses to this and becomes simply up-down, in which case B, of course, is now definitely pointing down in the negative z direction. This means that the probability that B will be measured as -1 by this device, which is at theta to the z-axis, is cos squared theta over 2. Again, that is a standard result from what we have previously discussed. This means that the total probability for getting 1 for A and -1 for B when electron A is measured first in this setup is therefore the multiplication of these two probabilities, 0.5 times cos squared theta over 2. Now imagine exactly the same pair of entangled electrons, but this time imagine that B is measured first. Measuring B as the first of the entangled pair means that the probability for it to be measured as -1 in the direction of theta to the z-axis, i.e. in the negative theta direction, is 0.5. Once again, this is standard for the singlet state because it can legitimately be written like this, where the half can once again be clearly seen from the square of 1/√2, the coefficient. After that measurement, and finding B to be in the negative theta direction, the state collapses to this. This means that the A electron, which had no direction before, is now pointing in the positive theta direction. That means that when A is then measured second in the z direction, the probability that it will be measured as +1 in the z direction will be cos squared theta over 2, because the A spin is now at an angle of theta to the z-axis. So once again, we find that the total probability for getting A as 1 and B as -1 is therefore the multiplication of these two probabilities, which is 0.5 cos squared theta over 2. In other words, in each case, whether we think in terms of A being measured first or B is measured first, the probability of getting A measured as 1 in the z direction and B measured as -1 in the theta direction is exactly the same. As regards the experimental outcome, there will be no difference, and this will be true for any pair of measurements made on electrons A and B at any angles. So that's it, in one sense. We're all done with entanglement of a pair of electrons, at least as far as I'm concerned. The singlet state is king, whichever way you choose to write it, and this state vector helps to explain what's going on when measurements are made. What we haven't yet looked at, of course, is any other ideas that might help to explain what's going on. Maybe it's not really all about quantum mechanics. Maybe there are classical ideas and models that could equally well explain all the results that we've been discussing so far and all of the probabilities. And this was the great debate in physics in the early 20th century. And it wasn't until the latter part of that century that experiments could be done to help to decide between certain models and ideas. Needless to say, quantum mechanics came out on top, but something of the story is nevertheless worth telling, and it will involve something called Bell's inequality. The next few videos will discuss some of those alternative models, and we will first look at Bell's inequality and then think through the kinds of experiments that help to dispense with some of those other models to leave quantum mechanics as the most popular explanation of the physics of the very small.